this video is our introduction to 9.4.4 superconductors, and we're going right back to the beginning of the theory of conductivity. And the theory of metal conductivity and the theory of superconductivity relied upon our understanding of the crystal structure of solids, and it was because of the work of two Australian physicists who received the 1915 Nobel Prize in Physics, the way they used X-ray diffraction to determine the spacing of atoms in crystals and let us learn about atomic structure and learn about crystal structure. And therefore, because of their work, we now have a better understanding of how things conduct. So what did they do? What they did was something called X-ray diffraction. Now, we know these days that crystalline solids such as metals exist as a regular three-dimensional arrangement of atoms in a lattice, but there was no way at that time of actually measuring how far apart atoms were because the spacing was so tiny there was no way of observing it. But what the Braggs did, William and Lawrence Bragg, the two Australian or English-Australian scientists who won the Nobel Prize, they used X-rays to try and measure the distance between atoms and solids. And they did that using something called X-ray diffraction. Now, before we go into what they did, it's important we revise what diffraction is. We learnt this in the preliminary course, but here it is again. Diffraction is a name given to the phenomenon in which a wave spreads out as it passes through a small aperture or around an obstacle. And the interference or superposition of diffracted waves produces something called a diffraction pattern. Now, that definition there has got to go into your notes. It's on page 2 of your notes. There's a gap at the top where that goes into. But what does that mean, a diffraction pattern? Well, there's a couple of pictures here which are also in your notes, and what it's showing is waves diffracting. In this picture on the left-hand side, we've got a series of wave fronts coming in. So we're looking down on top of the waves. Imagine this is looking down on top of the beach and seeing the waves heading towards the beach this way, and these lines represent the wave fronts. As this wave hits an obstacle, and here we've got an obstacle here with two openings in it, as it passes through these two openings, at every opening it's diffracted, therefore it spreads out, and once again in spherical sort of waves from each opening. Because we've now got two sources of waves, one for each aperture or one for each opening, those waves interfere with each other, and depending on whether they're in phase or out of phase, they'll either constructively or destructively interfere. So at certain places along the way, they'll be in phase and constructive interference, and here you have a quite large amplitude of wave here, here, and here. But in some places they're completely out of phase, and that means here, here, and here, and here, for example, they'll be completely destructively interfering with each other. Therefore, you get no amplitude in these spots. And therefore, depending on where you are along this region here, you'll either see high amplitude waves or no waves at all. In this picture, again, just another picture from the side. Looking again, here's the wavefronts, here's the apertures, here's the splitting out of the waves. Here is a detector or screen, and showing it's got a bright white stripe here where you have constructive interference, and a dark stripe where you might see destructive interference. So that's what the point of a diffraction pattern is. And what the Braggs did, we're going to find in a minute, was they used the spacing between these bright and dark spots, or constructive and destructive interference, to figure out how far apart the aperture must have been, and because the aperture in this case was atoms in a crystal, how far apart the atoms must have been in the crystal. And a little image of this, here's just a moving picture of what we're seeing here. Here are two sources of light. They're both interfering with each other. This could be two sources of light coming out of light reflecting off a crystal or from two apertures. And here this screen is a detector, and obviously the detector, where there's constructive interference, you get a nice bright spot here, and where there's destructive interference, you get a dark spot, a low intensity here, and you can see those patterns coming out of interfering with each other. So once again, and this goes to the bottom of page 2, it says the British and Australian physicists William and Lawrence Bragg, father and son, applied X-ray diffraction to the study of crystals from about 1912 onwards. And what's what they did? A beam of X-rays with a wide range of wavelengths was collimated, which means passed through a device that ensured all X-rays are parallel, and directed onto a single crystal specimen under study. A flat film behind the specimen received the diffracted beams. The diffraction pattern consisted of a series of spots of light that indicated the symmetry of the crystal. So a series of spots of light means where you've got this constructive interference, they show bright spots or light on the screen in certain spots, and dark spots where there's destructive interference. So what they do, here's your X-ray source. Here's your collimator. It's just a device to ensure that all the X-rays that actually hit the sample are going in a straight line. In my example, it's a long, thin tube. Therefore, the only X-rays that can actually get through the tube are the ones traveling parallel. Here's our single crystal sample we're studying. The X-rays hit the sample. They're diffracted off the crystal, and therefore only certain places you've got constructive interference, and therefore only certain places you see a bright spot on the photographic film. Just a quick example of that. Let's see here. Here is an example. Here is our collimated X-ray beams. Here is our crystal. These two lines represent the spacing atoms in the crystal. And depending on how far apart those atoms are, you'll get different diffraction patterns. So if I change the spacing between the slits, which is like changing the size of the atoms in the crystal, if they're very close together or very far apart, we get different patterns. And what the Braggs do, by measuring the distance between these spots and exactly where these spots were, they'll be able to use mathematics to figure out how far apart the atoms must be in the crystal. Now, if we go on to page 3 now, at the top of the page says William Bragg presented a simple explanation for the diffracted beams, but he thought about, on the atomic scale, what does it mean for these beams to be diffracted? And he suggested the X-rays were incident on the parallel planes of atoms, so these lines here represent planes of atoms in the crystal. And he said that the X-rays were reflected off each plane of crystals, and each plane only reflected some of the X-rays. And the diffraction patterns you got were formed when the reflections of the different planes were either constructively or destructively interfering with each other. So here you have a whole lot of X-rays coming with the crystal. Some reflect off its first plane of atoms, some penetrate through because X-rays are highly penetrating and reflect off the second plane of atoms, some reflect off the third plane of atoms, and so on. And depending on if they were in phase or out of phase when they're reflected, depending on whether you have constructive or destructive interference. The mathematics and the genius of this was they actually figured out the relationship would be when they were constructively interfering. So if you think about these two X-rays coming in, and right now they're coming in phase, the peaks and the troughs are actually in line with each other. There's the X-rays from the X-ray source. This one strikes the crystal here, and when it strikes the crystal and reflects, that's when this wave here has only reached this far. Now, in order to actually reflect off the next plane, this wave has to actually travel this much further, and it's also going to travel this much further again until it's back in the same alignment as the first wave. And therefore, it's got a path difference. This region here, I'm going to highlight it in pink. That's probably a bit too big a highlighter. So this region here, I'll do it in green now, it seems. This region here is the path difference that the two waves travel. This one travelled this extra distance compared to that one. And the Braggs realised that the only way they'd be in phase was if that path difference was an exact number of wavelengths, so that they would come out in exactly the same phase as this wave here. And the path difference, this little side here, if the wave's coming in at angle theta, that angle there is also theta. That distance there, the hypotenuse of this particular triangle is d, and therefore this distance here is d sine theta. So therefore the total path difference for the two waves was 2d sine theta. And they said the only way you get constructive interference is if this 2d sine theta was a whole number of wavelengths, so it would come out exactly in phase with this first reflected wave. And that was put together in what's called Bragg's law, and that goes into space on page 3 as well. Bragg's law just says 2d sine theta must equal n lambda, i.e. that path difference, 2d sine theta, must be an integer number of wavelengths or a whole number of wavelengths. And that's when you get constructive interference. So by doing your experiment, figuring out where the bright spots were, figuring out the angles where you got bright spots, you'd be able to figure out this value d, which is the atomic spacing, because you knew the wavelength of the waves you're shining in. N will just represent the number of different spots you got, theta will represent the angle you measured from the experiment, and d will therefore be the atomic spacing. And that was incredibly important for physics. A knowledge of atomic spacing led to understanding of the mechanical, chemical, electrical, magnetic properties of materials, and once you knew that, you could actually tailor materials to produce desired mechanical, chemical, electrical, magnetic properties. So it was very important for material science, but also very important for analytical science, because you could then analyse materials to figure out their composition and atomic spacing. And one of the most famous examples was when Rosalind Franklin used X-ray diffraction to figure out the structure of DNA by producing this lovely X-shaped diffraction pattern. So there we have it. That is how the Braggs applied X-ray diffraction to crystals, and we were able to learn about atomic spacing from their experiments. There was one more little video I was going to show you. It's this one here. Just an example. Here's some X-rays coming in to some crystal planes, and right now you can see the two waves. They're coming out. They're pretty much not in phase. They're destructively interfering with each other. What we can do is put this up here. If we start changing our angle, we can see that those two waves, as shown on the screen here, depending on the angle, they go from being destructive interfering to constructive interference. That means at this angle here, 28 degrees, we get a bright spot on the screen, keep moving forward again, getting more and more out of phase, get to an angle such as like 47 degrees, we'd see a dark spot on the screen. So we're looking at the angles where you've got light and dark spots. You could tell they're in phase or out of phase, and therefore figure out the atomic spacing using the Braggs law.